Okay, let's start. So this is the condition for non-ideal solution. Am I audible to you?
Yes, sir.
So you can see that ideal solution and non-ideal solution, we categorize it. Ideal solution which follows Rolle's law: delta V mix 0, delta H mix 0, and delta G less than 0 and delta S greater than 0 in both the cases, whether it is ideal and non-ideal. Also, the interaction between pure A particle and the interaction between pure B particle will be equal to the interaction between solution particle AB. This is the condition for ideal solution. Now come to the non-ideal solution. Non-ideal solution which does not follow Rolle's law: delta H mix, delta V mix not equals to 0, delta H mix not equals to 0, delta G less than 0, delta S greater than 0. And the fifth condition is the particle interaction of particle between A particle and B particle will not be equal to the interaction of particle in the solution AB. So this was it for the last class, from the last class. Now going to start. Basically, there are two types of non-ideal solution, that is positive deviation or negative deviation. So I'm going to classify non-ideal solution in two parts. So the first part is basically non-ideal solution showing positive deviation, showing positive deviation, and non-ideal solution showing negative deviation, showing negative deviation. Are you getting my point?
Yes, sir.
Now see how we are going to classify whether non-ideal solution showing positive deviation or negative deviation. So there are conditions for that. In this case, non-ideal solution, we just know not equal to uh, not equal to 0, not equal to 0, and not equal to AB interaction. Here, non-ideal solution with showing positive deviation will have PT, that means total pressure, greater than partial pressure of PA plus PV. That means calculated total pressure will be greater than observed total pressure. Is that clear?
Yes, sir. Meaning the
It-
product is greater.
yeah. PT total pressure greater than P naught A zeta A plus P naught B zeta B. This second condition is in the non-ideal solution, delta V mix not equals to 0. So basically, delta V mix showing positive deviation greater than 0, not equals to 0. Here will be positive deviation greater than 0. In the same way, we can go for delta H mix not equals to 0 and in positive deviation greater than 0. The fourth one is same, like delta G less than 0 and delta S greater than 0. And the fifth condition, which is very important for the classification, fifth condition is the interaction between pure particles will be greater than interaction between solution particles. That means the vapor pressure of the solution will be lesser than the vapor pressure of the pure components. The interaction, the force of attraction in pure particle is greater. The force of attraction in pure particle of B is greater. If force of attraction is greater, then vapor pressure will be lower or not? The vapor pressure will be lower.
Yes.
So we can say that basically the vapor pressure in solution will be higher than vapor pressure in pure particles. Madhya, is that clear to you also? Madhya?
Yes, sir, it is clear.
Okay. Now going for showing negative deviation, showing negative deviation. So for negative deviation, it is opposite, like PT less than PA plus PB, or we can also write PT less than P naught A zeta A plus P naught B zeta B. The second condition, when we talk about delta V mix, it will be lesser than 0. The third condition, delta H mix will be lesser than 0. The fourth one is delta G less than 0 and delta S greater than 0. The fifth condition is A particle has the interaction between A particle and the interaction between BB particle will be lesser than interaction between AB particle. That means the solution's particles are tightly bonded with higher force of attraction than the pure particle. That means vapor pressure of solution in negative deviation will be lower than the pure one. Is that clear?
Yes, sir.
Very good. Thank you. So please write it. Then we are going to plot a graph for positive deviation as well as negative deviation with reference to ideal solution. So can anyone arrange previous year's question? Rim, Madiha.
No, sir, I wasn't able to get it because my exams just started, so I'm busy with that. Once it gets over,
Sir, same.
Okay.
Even my exam started, so I don't have time.
Okay. Look, yeah, and here we got a sample paper like you like and together with lots of sample paper, including in that book there will be previous year's question too. Okay, uh, in your school or in your nearby, does they give any previous year's sample paper?
Sir, we do those questions at the end of the chapter mostly, or like at the end when we complete the syllabus.
Okay, from the school you got it.
No, sir, we didn't get it, but we will get it later, not now.
Okay. Please write it and let me know. Let me know when you are done with this. Wait a minute.
Done, sir.
Done, everyone. Madiha.
Done, sir.
Okay. Now we are going to have a graph on positive deviation as well as negative deviation with the reference to ideal solution. So here we already know this graph. Basically here pure A, that's why zeta A is equal to 1 mole fraction of A, and mole fraction of B will be 0. Again mole fraction of B will be 1 because only B is present here, and mole fraction of A is equal to 0. This is basically mole fraction. So this is mole fraction and this is vapor pressure. And since only A is present here, so it will have a T naught A here and B is P naught B here. You can take it PV P naught B upper than A in P naught A, as I considered P naught A since A is having more vapor pressure. That means A is more volatile. Now, according to Rolle's law, we plot a graph like this and also like this. Now see, we are going to join this. So it will be basically total pressure. This is the condition for, this is for ideal solution. Now, when we talk about positive deviation, that means this will have more vapor pressure. This will have more vapor pressure. That's why total vapor pressure will be also more. So it will be upward positive. So this is PT, this is PA, this is basically this is PB, and this is P. So this graph is for positive deviation. In the same way, if we are going for negative deviation, if we are going for negative deviation, zeta A is equal to 1, zeta B is equal to 0, zeta B is equal to 1, zeta A is equal to 0. Again, this is P naught A, this is P naught B, and this is the graph for this is the graph for ideal solution. And again, if you are going to make this is for ideal gas. But when we talk about negative deviation, the vapor pressure will be lower, so the graph will be like this, and like this. Total vapor pressure will be also decreased. So this is basically for PT, this is for PB, and this is for PA. Please write it. Please do it, and if you're done, let me know.
Done, sir.
Done, everyone.
Yeah, done, sir.
So this is the graph for positive deviation. This is the graph for negative deviation. Now, how we are going to find out whether solution is ideal and non-ideal solution by just looking at it, or by knowing the name. So there is a trick. Generally, we know it by doing experiment like which one have more vapor pressure, which one have lesser vapor pressure. On that base, we classify. But for the questions you will be asked in the exams. See, I'm going to classify it in two parts. This is basically ideal solution. I will give some tricks so that you will be able to solve it. And this is non-ideal solution. This is non-ideal solution. So this is non-ideal solution. There are two parts in non-ideal solution. The first is positive deviation, non-ideal solution showing positive deviation, and the second one is showing negative deviation. Negative deviation. Now see how we are gonna recognize whether a solution is ideal solution or whether a solution is non-ideal solution with in positive deviation or negative deviation. So always remember, generally it happens that an ideal solution is one which are similar. The soluble, basically the solute and solvent will have similarity between them. Like example, I am going to take just suppose n-butyl chloride, n-butyl chloride plus n-butyl bromide, n-butyl bromide. So you can see there is similarity like butyl butane, 4 carbon is here, 4 carbon is here, chloride and bromide, that means that means basically halogens are here, halogens are there, that shows ideal solution. So whenever a solution given with a solute and solvent name and there will be similarity, that will be ideal solution. Got it, Rim?
Yes, sir.
So Madhiha, you are disconnected, right? Ideal solution are the one you can recognize it. If there is similarity, that will be ideal solution. Second, I am going to take an example like ethyl bromide plus ethyl iodide. So you can see that there is similarity. So if there is similarity, that will be ideal solution. Again, chlorobenzene plus bromobenzene. Since both have benzene, so it will be ideal solution. Fourth, you can take example N-hexane, normal hexane plus N-heptane. Basically, both are saturated hydrocarbon, and hexane and heptane saturated hydrocarbon. That shows it is similar. That's why they are ideal solution. This is the trick for finding, recognizing whether it is ideal and non-ideal solution. See, non-ideal solution positive showing positive deviation are the one in which generally there are alcohols. There will be alcohols. Like if you are going to take an example, you can take methanol plus water. Alcohol is there. There will be some exception. You have to learn it. Remember it. Methanol plus water. Ethanol plus water. Ethanol plus cyclohexane. Cyclohexane. Acetone plus CS2. You have to remember it. Acetone plus CS2. And then acetone plus ethanol. Acetone plus ethanol, there is alcohol, so it will show it is non-ideal solution with negative positive deviation. How we are gonna recognize whether it is negative deviation? Generally there will be acid present in it. There will be acid present in it. Just suppose like HCl plus H2O, hydrochloric acid plus water, HNO3 plus H2O. That means acid plus water. HCOOH, methanoic acid plus water. So there is acid. Also CH3, ethanoic acid plus water. CHCl3, chloroform plus benzene. You have to remember it, C6H6. CHCl3, that means chlorobenzene, chloroform plus benzene. You have to remember it. Next, CH3COOH, ethanoic acid plus pyridine. Ethanoic acid plus pyridine will show negative deviation. Also, methanol, that means CH3OH plus CH3COOH. This is alcohol and acid, both are present, but this solution shows negative deviation. Also, the last I'm going to write it here for negative deviation is CH3COCH3, that means propanol, ketone plus aniline. Ketone plus aniline. So this also shows negative deviation. So these are almost all the list that questions will be asked from this. Or apart from this, if there will be question, you can go for similarity, alcohols for positive deviation, acid for negative deviation. I also marked a star. They are different but shows positive deviation or negative deviation. So you have to remember it.
Sir, can I write this down?
Yes, yes, you should. You must.
Okay.
Please write it down. I'm waiting.
Done, sir.
Very good. Everyone done with this? So this is it for. Is the screen shared with question? Is a new screen shared?
Yes, sir.
Reem,
Yes.
Madiha. So can you read it? Basically this one. Topic 2, vapor pressure, laws of solution. Is this visible, right?
Yes, sir.
Oh, so question number 14, you are going to attempt it. So we are going to have some questions. The mixture which shows positive deviation from Raoult's law. What is the trick for positive deviation with Raoult's law? Positive deviation, that means there must be an alcohol. What do you think? Is there any alcohol? No. Is there any alcohol? See, what is the answer? There were exception also. So you have to keep it in mind and solve the question. Tell me.
Option D.
Option D. Any answer from Madiha?
Sir, is it option B?
B. Can you check your notes?
Sir, it's D.
Oh. Wait a minute. So did you check it?
Yes,
Madhya?
it's D.
It's D, right? So it's very easy. So go for alcohol first, and the answer will be D. Very good. Very good. Can you solve this question number 22? Please do this practice, then we will move to colligative property, a new topic for today.
Sir, is it option C?
Option C. No, I think the option. What is your answer? 347.9 mmHg.
Yes, sir.
I think it's wrong answer. Madhya? Okay, tell me. Basically, there is a question: vapor pressure of chloroform and dichloromethane at 25 degrees centigrade are this and this. That means they are individually. That means basically they are talking about pure vapor pressure. P naught is given. Okay. Now see, vapor pressure of the solution. PT is also vapor pressure of the solution obtained by mixture of this at the same temperature will be. At PT we need to calculate PT. PT will be equal to, you know that PT will be equal to, wait a minute. PT will be equal to PA plus PB. We can take PA plus PB, A for chloroform and B for dichloromethane. Okay. So you can easily calculate chloroform. I am going to represent it by C, not A, C, and then dichloromethane D. So you can see PC will be equal to P naught C into zeta C. What is the pure pressure of P naught C is given 200. And can you find the mole fraction of chloroform? What is the mole fraction of chloroform? Anyone?
Sir, is it 1.67?
Sir, is it 0.47?
47 for chloroform. Wait. Have you written the question?
Yes.
Okay. And then help me. Okay. Okay. Let me know the number of moles of chloroform. Given mass is how much? 25.5, right?
Yes.
Madhya. And molar mass is also given 119.5. And if you are going to divide it, it will be 0.213. 0.21 you can take. And if you are going for moles of dichloromethane, Given mass is basically 40 and molar mass is 85. So it will be 0.47. This is number of moles. This is number of moles. So if you are going to calculate mole fraction of CHCl3 chloroform, mole fraction of CHCl3, it will be 0.213. It will be 0.213 upon 0.213 plus 0.47 plus 0.47. Okay.
Sir, it
So
is
mole fraction.
1.47 for
No.
chlorophyll.
What mole fraction? Are you talking about mole fraction?
Yes, sir.
Mole fraction cannot be greater than 1. Just keep it in mind. Okay. So this is the mole fraction, basically 0.213 divided by 0.213 plus 0.47, because it's fraction. It won't be greater than. Are you getting my point?
Yes,
And
sir.
if you are going to divide it 0.213 divided by 0.683, so it will be 0.31. Again, if you are going to find the mole fraction of CH2Cl2, the value are uneven, that's why it's taking time. 0.47 upon 0.47 plus 0.213. So it will be basically 0.47 upon 0.683. So if I'm going to divide it, 0.47 divided by 0.683, it will be 0.69. This is the mole fraction. Now come to the main point. Partial pressure of chloroform will be pure vapor pressure. What is the pure vapor pressure of this is 200 into mole fraction 0.31. And partial pressure of CH2Cl2. What is the pure pressure of dichloromethane? It was given in the question. Tell me.
41.5.
41.5 into 0.69. Sorry. Yes. 0.69. And we need to calculate PT. So what we need to do is partial pressure of chloroform plus partial pressure of dichloromethane. So calculate it and just solve the value. You will get your answer. 200 into 0.31. So it will be nearly 62. And if you are going to solve it, 41.5 into 0.69, it will be 28.635. So if you are going to add 62, you will get 90.6
Sir, it's 90.6.
mmHg. Yes, and these are not available in the option, right? This is not available in the option. Is there any option? 90.
No, sir.
Okay. So none of these the answer. So please do it and let me know if you're done with this. Then we are going to start qualitative property. Are you done with this?
Yes, sir.
Okay, Rim.
Yeah, I'm done.
Okay. Now going to start another topic, colligative property. And colligative property is very important for this chapter, and it's very easy. So first of all, what is colligative property? Property of any dilute solution which depends on the number of solute particles. That depends on how many number of solute particles are there. That is called colligative property. Colligative property does not depend on the nature, it depends on the number. So I'm going to define it. Those property of dilute solutions which depend upon number of solute particles, and not on the nature of solute particles, That is called colligative property. This is very important. Those property of the dilute depend upon number of solute particles, which depends upon number of solute particles. That is called colligative properties. There are four colligative properties that we need to study. The first one is relative lowering in vapor pressure, that we already have done. Relative lowering in vapor pressure. Then elevation in boiling point. Then depression in freezing point. Then again called osmotic pressure. So please write all this list and let me know when you are finished.
Done, sir.
Very good. Both of you done? Madhya?
Yes, sir.
Now going for the first one, a relative lowering in vapor pressure, that we have already derived. Relative lowering in vapor pressure. So basically this term was already introduced when we did vapor pressure of solution containing non-volatile solute. So mole fraction of solute will be equal to total original pressure of A minus partial pressure of A upon original pressure of A. This is the mole fraction of solute, and this is the formula for relative lowering in vapor pressure, in which I told you that only the numerator part is called lowering in vapor pressure, but when we divide it by the original pressure, we got a relative lowering in vapor pressure, also known as Rlvp. So please write it, and then we are going to derive for elevation in boiling point, and then depression in freezing point, and then osmotic pressure. Are you done with this?
Done, sir.
Done, sir.
Very good. Now see, this is the case when solute is non-volatile. That means they are in solid state. Like you use urea, that is non-volatile solute, sugar, that is non-volatile solute, and glucose like this, etc. This is the condition for that. So second colligative properties is elevation in a boiling point. This will be clear when I told you that when we saw vapor pressure of solution containing non-volatile solutes. So at that time, you both have answered me that this is A, so this is P naught A, and this is B, that is non-volatile solute, and mixed in a bigger container, A, B, A, B. This is basically PA, partial pressure of A. So you have answered that P naught A greater than PA. Yes or no?
Yes.
So basically what I am trying to say is that vapor pressure of this is greater than vapor pressure of this solution. So can you think it of in terms of boiling point? The particle or substance that gets easily vaporized will have lower boiling point, or the particles which get a little more time to vaporize will have more boiling point. Yes or no? Rim, Madiha, if vapor pressure is greater here 1 than 2, then boiling, if you are going to compare boiling point between 1 and 2, then 2 will be greater than 1 or not? Answer me. Think about
Yes,
it
sir.
and let me.
Yes, sir.
So basically, whenever we are going to add non-volatile solute, there will be elevation in boiling point. That means solution will have more boiling point, than pure solvent. Are you getting my point? Yes or no?
Yes, sir.
Okay. So here is solvent that is volatile, and we are going to add non-volatile solute. So what happens here, whenever we are going to add non-volatile solute, vapor pressure will decreases and boiling point will increase. Are you getting my point? Vapor pressure will
Yes, sir.
decrease. Like the previous one, original has more vapor pressure than solution. So vapor pressure will decrease and boiling point will increase. Also, we are going to define boiling point. What is exactly boiling point? So the temperature at which vapor pressure of solution will be equal to atmospheric pressure. The pressure exerted by atmosphere, that is called atmospheric pressure. If that pressure, atmospheric pressure, will be equal to vapor pressure, that temperature is called boiling point. So I'm going to write the temperature at which vapor pressure of solution becomes equal to atmospheric pressure, becomes equals to atmospheric pressure. That temperature is called boiling point. Please write it, and then I'm going to draw a graph for solvent as well as solution, and then we are going to derive a formula and do questions on this. Please do it. Let me know when you are done with this.
Done, sir.
Very
Done,
good.
sir.
Very good. Now see, I'm going to plot a graph. This is graph between temperature and vapor pressure that we have already done like this. This is the graph for vapor pressure of any substance and versus temperature. So basically in this graph, I'm going to plot for solvent as well as solution. So this is for solvent. If I'm going to plot a graph, this is for solvent and it is vaporizing T not B, not that represents pure. And when we talk about solution, solution will have more boiling point. So it will be TB. This is the boiling point of solution. This is for solution and this is for solvent. This is for solution and this is for solvent. You can see this TB is boiling point of solution, which is more than boiling point of pure solvent. Now we are going to calculate delta TB. Delta TB is equal to TB minus T naught B. I will write all this, which is what, and by experimentally, it was found that this delta TB directly proportional to molality. This delta TB directly proportional to molality. And to remove this proportionality sign, we have a constant that is called molal elevation constant Kb. This is molal elevation constant, also known as ebullioscopic constant, also known as ebullioscopic constant, also known as ebullioscopic constant. So this is the formula for this, and here I'm going to write TB is basically boiling point of solution. TB is basically boiling point of solution. T naught B is basically boiling point of pure solvent. And Kb I already wrote, which depends on nature of gas and solvent and also temperature. So please write it and let me know the unit of Kb. You can easily calculate. Let me know when you're done with this.
Done, sir.
Both of you done?
Yes, Lady.
Okay. Tell me the unit of KB. Can you calculate KB, a unit of KB? You have formula you can
Sir,
easily
it's
calculate.
kg mole raised to the power minus 1.
No, wait a minute. Again, tell me. kg,
Mole raised to the power minus 1.
like this.
Yeah.
See, delta TB is equal to, I just wrote KB into M. Okay. We need to find the unit of KB. KB will be delta TB upon M. Yes or no? Now,
Yes, sir.
TB, delta TB, change in temperature, has a unit Kelvin upon molality, that is mole per kg. So this kg will go upward in numerator. Kelvin kg per mole is the unit. You forgot to tell me about the Kelvin. This is wrong. Okay.
Okay, sir.
Madhya,
Yes, correct.
very good. I'm going to change the, can I change the slide?
Yes, sir.
Okay. So I'm going to give you a question. 18 gram of glucose dissolved in 1 kg of water. Calculate boiling point of solution if boiling point of water is 373 Kelvin and Kb for water is 0.52 Kelvin kg per mole. Please solve it. Done.
I'm still doing, sir.
Okay. Done, everyone.
Sir, is it 373.202 Kelvin?
373.052 Kelvin. See, 18 gram of glucose dissolved in 1 kg of H2O. Calculate boiling point of solution. Boiling point of solution in boiling point of water, that means pure solvent is given 373 Kelvin, and Kb for water is this. Madhya, what about you? Delta Tb is equal to Kb into m. Now see, Kb has a value 0.52, and molality, that means number of moles of solute. You can easily calculate number of moles of solute, that is
Sir,
given
I
mass
have
upon molar mass.
373.52.
Okay, I will see it. 0.1. This is 0.1 mole divided by solvent. Number of moles of solute upon mass of solvent, that is 1. So the value will be 0.052. Yes or no? Is this
Yes, sir.
correct? Now see, delta Tb has a value, that is Tb, boiling point of solution, minus boiling point of solvent. Boiling point of solution minus boiling point of solvent. This has a value 0.052, and this is basically solution. We need to calculate the boiling point of solution minus boiling point of solvent, that is given 373. And when we move this to the left hand side, Tb will be equal to 0.052 plus 373. That will have a value 373.052 Kelvin. Got it?
Yes, sir.
Okay, please do it. Let me know when you are finished.
Done, sir.
Madhya, are you also done?
Yes, sir, I'm done.
Now see, basically this is, wait a minute. Okay. Now the next colligative properties come to out to be the third one. Depression in freezing point. Depression in freezing point. That means when a volatile solvent, when a non-volatile solute is added to a volatile solvent, the depression, basically the freezing point decreases. The freezing point decreases. So first of all, I'm going to define some terms like freezing point. So what is freezing point? It is the temperature at which the vapor pressure of liquid state becomes equal to the vapor pressure of solid state. So this is the temperature at which vapor pressure of liquid state is equal to vapor pressure of solid state. That temperature is called freezing point. So first of all, you are going to write this definition, then I'm going to plot a graph, and then we will derive a formula and practice a question. Madhya, are you also done?
Yes, sir, done.
So basically, when we add non-volatile solute, the depression in there will be depression in freezing point. That means solution will have lower freezing point as compared to the pure solvent. So I'm going to plot a graph, the same graph basically for freezing. This is for temperature. This is for vapor pressure. And the graph will be like this. This is basically frozen solvent. This is the for frozen solvent. And this is basically for liquid solvent. Liquid solvent. And this is the point for solution. Now you are going to understand it. What I have plotted is this is the temperature for the freezing point of pure solvent, T naught F. And this is the temperature at which solution is freezing. You can see the solution's freezing point is lower than the pure solvent freezing point. This is the graph. Now see this, the difference between this is called delta TF, and experimentally we found delta TF is basically pure solvent freezing point minus solution freezing point. And experimentally, delta TF directly proportional to molality in the same way as the previous one. This small m represents molality. And if we are going to remove the proportionality sign, we will have Kf, that is cryoscopic constant and molar depression constant, also known as this is constant, cryoscopic constant, or molar depression constant, and it depends on the same way as Kb depends, and you can calculate the unit of K. Please do it and let me know if you are finished with this.
Done, sir.
Both of you done with this?
Just a minute, sir.
Okay, take your time.
Done, sir.
Very good. I'm going to give you a question on this. Question is, what amount of C2H5OH ethanol assumed to be non-volatile must be dissolved in 1 kg water. In 1 kg water, so that it freezes. It freezes at -2 degrees centigrade. And here it is given that freezing point of water is 0 degrees centigrade, and also Kf equals to 1.86 Kelvin kg per mole. Did you find the unit of Kf? Yes or no? Rin, Madiha. Have you calculated the unit of Kf? Yes or no?
No, sir.
You should first of all calculate the unit of Kf, that is cryoscopic constant or depression constant. You can easily calculate it.
Sir, it will be the same as KB, Kelvin.
Yes,
not a mole.
Kelvin
Yes, sir. It's the same.
kg per mole. Very good, very good. Thank you. Please do this question. Are you able to solve it, or do you need any type of assist?
Sir, can you do it?
Yes, I can do it. Madhya, what about you? See,
Sir,
so
please.
simple it is. Okay. See, it's very simple. What amount of C2H5OH? That means mass of C2H5OH has been asked in the question. To be non-volatile must be dissolved in 1 kg of water. That means mass of solvent is given as 1 kg. So that it freezes at -2 degrees centigrade. After adding, it should be freezes at -2 degrees centigrade. Freezing point is given as pure freezing point 0 degrees centigrade, and Kf is 1.86 Kelvin kg per. So delta Tf is equal to, you can see, Kf into M. Kf into M. Kf has a value 1.86, and I am just supposing M as M is what? M is molality, and delta Tf has a value Tf minus T naught F. I'm sorry, T naught F minus Tf. This is the formula, yes or no? Tell me. This is the formula.
Yes, sir.
T naught F, that means pure solvent has a vapor, has a value 0 minus Tf, that means after solution's freezing point is -2, will be equal to 1.86 into M. And M will have a value 0 minus into minus plus divided by 1.86. Can I write this? Yes or no?
Yes, sir.
And molality has a formula, number of moles of solute upon mass of solvent in kg, that will be equal to this is 2 upon 1.86. Now see, number of moles of solute, that is given mass that we needed to calculate upon molar mass. Molar mass of C2H5OH. Can you tell me? Molar mass of C2H5OH will be 46. Mass of solvent is given as 1 kg, will be equal to 2 upon 1.86. 2 upon 1.86. I'm doing it step by step. You can easily understand it. Now see, M by 46 will be equal to 2 upon 1.86, and M will be equal to 46 into 2 upon 1.86. Can't you calculate it? 46 into 2 divided by 1.86, that will be equal to 49.46, that means 49.5 grams. Isn't it easy?
Yes, sir.
So you just have to understand the language of question. If you know the formula or your basics are good, then you can easily do it. Easily. Just write it and let me know when you are finished. And then I'll see you in the next class.
Done, sir.
Very good, Madhya. So this is it for today. Thank you so much. Please do questions from NCERT as well as from your assignments. And if you got any previous year's questions, then let me know. Send it to me. Send it to the coaching's number. And
Sir,
one
thank you.
more important announcement is that there will be most probably test on Monday for half an hour, last half an hour. Okay. And the
Okay, sir.
syllabus will be solution. Okay.